Chapter 9 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 9. Performance Maneuvers. Performance maneuvers are used to develop a high degree of pilot skill. They aid the pilot in analyzing the forces acting on the airplane and in developing a fine control touch, coordination, timing, and division of attention for precise maneuvering of the airplane. Performance maneuvers are termed advanced maneuvers because the degree of skill required for proper execution is normally not acquired until a pilot has obtained a sense of orientation and control feel in normal maneuvers. An important benefit of performance maneuvers is the sharpening of fundamental skills to the degree that the pilot can cope with unusual or unforeseen circumstances occasionally encountered in normal flight. Advanced maneuvers are variations and/or combinations of basic maneuvers previously learned. They embody the same principles and techniques as the basic maneuvers, but require a higher degree of skill for proper execution. The student, therefore, who demonstrates a lack of progress in the performance of advanced maneuvers is more than likely deficient in one or more of the basic maneuvers. The flight instructor should consider breaking the advanced maneuver down into its component basic maneuvers in an attempt to identify and correct the deficiency before continuing with the advanced maneuver. Steep turns. The objective of the maneuver is to develop the smoothness, coordination, orientation, division of attention, and control techniques necessary for the execution of maximum performance turns when the airplane is near its performance limits. Smoothness of control use, coordination, and accuracy of execution are the important features of this maneuver. The steep turn maneuver consists of a turn in either direction using a bank angle between 45 to 60 degrees. This will cause an overbanking tendency during which maximum turning performance is attained and relatively high load factors are imposed. Because of the high load factors imposed, these turns should be performed at an airspeed that does not exceed the airplane's designed maneuvering speed, VA. The principles of an ordinary steep turn apply, but as a practice maneuver, the steep turns should be continued until 360 degrees or 720 degrees of turn have been completed. See Figure 9-1. An airplane's maximum turning performance is its fastest rate of turn and its shortest radius of turn, which change both airspeed and angle of bank. Each airplane's turning performance is limited by the amount of power its engine is developing, its limited load factor, structural strength, and its aerodynamic characteristics. The limiting load factor determines the maximum bank, which can be maintained without stalling or exceeding the airplane's structural limitations. In most small airplanes, the maximum bank has been found to be approximately 50 degrees to 60 degrees. The pilot should realize the tremendous additional load that is imposed on an airplane as the bank is increased beyond 45 degrees. During a coordinated turn with a 70-degree bank, a load factor of approximately 3 Gs is placed on the airplane structure. Most general aviation type airplanes are stressed for approximately 3.8 Gs. Regardless of the airspeed or the type of airplanes involved, a given angle of bank in a turn, during which altitude is maintained, will always produce the same load factor. Pilots must be aware that an additional load factor increases the stalling speed at a significant rate. Stalling speed increases with the square root of the load factor. For example, a light airplane that stalls at 60 knots in level flight will stall at nearly 85 knots in a 60-degree bank. The pilot's understanding and observance of this fact is an indispensable safety precaution for the performance of all maneuvers requiring turns. Before starting the steep turn, the pilot should ensure that the area is clear of other air traffic since the rate of turn will be quite rapid. After establishing the manufacturer's recommended entry speed or design maneuvering speed, the airplane should be smoothly rolled into the selected bank angle between 45 to 60 degrees. As the turn is being established, back elevator pressure should be smoothly increased to increase the angle of attack. This provides the additional wing lift required to compensate for the increasing load factor. After the selected bank angle has been reached, the pilot will find that considerable force is required on the elevator control to hold the airplane in level flight to maintain altitude. Because of this increase in the force applied to the elevators, the load factor increases rapidly as the bank is increased. Additional back elevator pressure increases the angle of attack, which results in an increase in drag. Consequently, power must be added to maintain the entry altitude and airspeed. Eventually, as the bank approaches the airplane's maximum angle, the maximum performance or structural limit is being reached. If this limit is exceeded, the airplane will be subjected to excessive structural loads and will lose altitude or stall. The limit load factor must not be exceeded to prevent structural damage. During the turn, the pilot should not stare at any one object. To maintain altitude as well as orientation requires an awareness of the relative position of the nose, the horizon, the wings, and the amount of bank. The pilot who references the aircraft's turn by watching only the nose will have difficulty holding altitude constant. On the other hand, the pilot who watches the nose, the horizon, and the wings can usually hold altitude within a few feet. If the altitude begins to increase or decrease, relaxing or increasing the back elevator pressure will be required as appropriate. This may also require a power adjustment to maintain the selected airspeed. A small increase or decrease of 1 to 3 degrees of bank angle may be used to control small altitude deviations. All bank angle changes should be done with coordinated use of aileron and rudder. The rollout from the turn should be timed so that the wings reach level flight when the airplane is exactly on the heading from which the maneuver was started. While the recovery is being made, back elevator pressure is gradually released and power reduced as necessary to maintain the altitude and airspeed. Common errors in performance of steep turns are failure to adequately clear the area, excessive pitch change during entry or recovery, attempts to start recovery prematurely, failure to stop the turn on a precise heading, excessive rudder during recovery resulting in skidding, inadequate power management, inadequate airspeed control, poor coordination, gaining altitude in right turns and or losing altitude in left turns, failure to maintain constant bank angle, disorientation, attempting to perform the maneuver by instrument reference rather than visual reference, failure to scan for other traffic during the maneuver. Steep spiral. The objective of this maneuver is to improve pilot techniques for airspeed control, wind drift control, planning, orientation, and division of attention. The steep spiral is not only a valuable flight training maneuver, but it has practical application in providing a procedure for dissipating altitude while remaining over a selected spot in preparation for landing, especially for emergency forced landings. A steep spiral is a constant gliding turn, during which a constant radius around a point on the ground is maintained. Similar to the maneuver, turns around a point. The radius should be such that the steepest bank will not exceed 60 degrees. Sufficient altitude must be obtained before starting this maneuver so that the spiral may be continued through a series of at least 3 360-degree turns. See Figure 9-2. The maneuver should not be continued below 1,000 feet above the surface unless performing an emergency landing in conjunction with the spiral. Operating the engine at idle speed for a prolonged period during the glide may result in excessive engine cooling or spark plug fouling. The engine should be cleared periodically by briefly advancing the throttle to normal cruise power while adjusting the pitch attitude to maintain a constant airspeed. Preferably, This should be done while headed into the wind to minimize any variation in ground speed and radius of turn. After the throttle is closed and the gliding speed is established, a gliding spiral should be started and a turn of constant radius maintained around a selected spot on the ground. This will require correction for wind drift by steepening the bank on downwind headings and shallowing the bank on upwind headings, just as in the maneuver turns around a point. During the descending spiral, the pilot must judge the direction and speed of the wind at different altitudes and make appropriate changes in the angle of bank to maintain a uniform radius. A constant airspeed should also be maintained throughout the maneuver. Failure to hold the airspeed constant will cause the radius of the turn and necessary angle of bank to vary excessively. On the downwind side of the maneuver, the steeper the bank angle, the lower the pitch attitude must be to maintain a given airspeed. Conversely, on the upwind side, as the bank angle becomes shallower, the pitch attitude must be raised to maintain the proper airspeed. This is necessary because the airspeed tends to change as the bank is changed from shallow to steep to shallow. During practice of the maneuver, the pilot should execute 3 turns and roll out toward a definite object or on a specific heading. During the rollout, smoothness is essential, and the use of controls must be so coordinated that no increase or decrease of speed results when the straight glide is resumed. Common errors in performance of steep spirals are failure to adequately clear the area, failure to maintain constant airspeed, poor coordination resulting in skidding and or slipping, inadequate wind drift correction, failure to coordinate the controls so that no increase, decrease in speed results when straight glide is resumed, failure to scan for other traffic, failure to maintain orientation. Chandelle. The objective of this maneuver is to develop the pilot's coordination, orientation, planning, and accuracy of control during maximum performance flight. A chandelle is a maximum performance climbing turn beginning from approximately straight and level flight and ending at the completion of a precise 180 degrees of turn in wings level, nose high attitude at the minimum controllable airspeed. See Figure 9-3. The maneuver demands that the maximum flight performance of the airplane be obtained. The airplane should gain the most altitude possible for a given degree of bank and a power setting without stalling. Since numerous atmospheric variables beyond control of the pilot will affect the specific amount of altitude gained, the quality of the performance of the maneuver is not judged solely on the altitude gain, but by the pilot's overall proficiency as it pertains to climb performance for the power bank combination used, and to the elements of piloting skill demonstrated. Prior to starting a chandelle, the flaps and gear, if retractable, should be in the up position, power set to cruise condition, and the airspace behind and above clear of other air traffic. The maneuver should be entered from the straight and level flight or a shallow dive and at a speed no greater than the maximum entry speed recommended by the manufacturer, in most cases not above the airplane's design maneuvering speed. VA. After the appropriate airspeed and power setting have been established, the chandelle is started by smoothly entering a coordinated turn with an angle of bank appropriate for the airplane being flown. Normally, this angle of bank should not exceed approximately 30 degrees. After the appropriate bank is established, a climbing turn should be started by smoothly applying back elevator pressure to increase the pitch attitude at a constant rate and to attain the highest pitch attitude as 90 degrees of turn is completed. As the climb is initiated in airplanes with fixed pitch propellers, full throttle may be applied, but it is applied gradually so that the maximum allowable RPM is not exceeded. In airplanes with constant speed propellers, power may be left at the normal cruise setting. Once the bank has been established, the angle of bank should remain constant until 90 degrees of turn is completed. Although the degree of bank is fixed during this climbing turn, it may appear to increase and, in fact, actually will tend to increase if allowed to do so as the maneuver continues. When the turn has progressed 90 degrees from the original heading, the pilot should begin rolling out of the bank at a constant rate while maintaining a constant pitch attitude. Since the angle of bank will be decreasing during the rollout, the vertical component of lift will increase slightly. For this reason, it may be necessary to release a slight amount of back elevator pressure in order to keep the nose of the airplane from rising higher. As the wings are being leveled at the completion of 180 degrees of turn, the pitch attitude should be noted by checking the outside references and the attitude indicator. This pitch attitude should be held momentarily while the plane is at the minimum controllable airspeed. Then the pitch attitude may be gently reduced to return to straight and level cruise flight. Since the airspeed is constantly decreasing throughout the maneuver, the effects of engine torque become more and more prominent. Therefore, right rudder pressure is gradually increased to control yaw and maintain a constant rate of turn and to keep the airplane in coordinated flight. The pilot should maintain coordinated flight by the feel of pressures being applied on the controls and by the ball instrument of the turn and slip indicator. If coordinated flight is being maintained, the ball will remain in the center of the race. To roll out of a left chandelle, the left aileron must be lowered to raise the left wing. This creates more drag than the aileron on the right wing, resulting in the tendency for the airplane to yaw to the left. With the low airspeed at this point, torque effect tries to make the airplane yaw to the left even more. Thus, there are two forces pulling the airplane's nose to the left: aileron drag and torque. To maintain coordinated flight, considerable right rudder pressure is required during the rollout to overcome the effects of aileron drag and torque. In a chandelle to the right, when control pressure is applied to begin the rollout, the aileron on the right wing is lowered. This creates more drag on that wing and tends to make the airplane yaw to the right. At the same time, the effect of torque at the lower speed is causing the airplane's nose to yaw to the left. Thus, aileron drag pulling the nose to the right and torque pulling to the left tend to neutralize each other. If excessive left rudder pressure is applied, the rollout will be uncoordinated. The rollout to the left can usually be accomplished with very little left rudder, since the effects of aileron drag and torque tend to neutralize each other. Releasing some right rudder, which has been applied to correct for torque, will normally give the same effect as applying left rudder pressure. When the wings become level and the ailerons are neutralized, the aileron drag disappears. Because of the low airspeed and high power, the effects of torque become the more prominent force and must continue to be controlled with rudder pressure. A rollout to the left is accomplished mainly by applying aileron pressure. During the rollout, right rudder pressure should be gradually released, and the left rudder applied only as necessary to maintain coordination. Even when the wings are level and aileron pressure is released, right rudder pressure must be held to counteract torque and hold the nose straight. Common errors in performance of chandelles are: failure to adequately clear the area, too shallow an initial bank resulting in a stall, too steep an initial bank resulting in failure to gain maximum performance, allowing the actual bank to increase after establishing initial bank angle, failure to start the recovery at the 90-degree point in the turn, allowing the pitch attitude to increase as the bank is rolled out during the second 90-degree of turn, removing all of the bank before the 180-degree point is reached, nose low on recovery, resulting in too much airspeed, control roughness, poor coordination, slipping or skidding, stalling at any point during the maneuver, execution of a steep turn instead of a climbing maneuver, failure to scan for other aircraft, attempting to perform the maneuver by instrument reference rather than visual reference. Lazy 8. The Lazy 8 is a maneuver designed to develop perfect coordination of controls through a wide range of airspeeds and altitudes so that certain accuracy points are reached with planned attitude and airspeed. In its execution, the dive, climb, and turn are all combined, and the combinations are varied and applied throughout the performance range of the airplane. It is the only standard flight training maneuver during which at no time do the forces on the controls remain constant. The Lazy 8 as a training maneuver has great value since constantly varying forces and attitudes are required. These forces must be constantly coordinated due not only to the changing combination of banks, dives, and climbs, but also to constantly varying airspeed. The maneuver helps develop subconscious feel, planning, orientation, coordination, and speed sense. It is not possible to do a Lazy 8 mechanically because the control pressures required for perfect coordination are never exactly the same. This maneuver derives its name from the manner in which the extended longitudinal axis of the airplane is made to trace a flight pattern in the form of a figure 8 lying on its side. A Lazy 8. See Figure 9-4. A Lazy 8 consists of two 180-degree turns in opposite directions while making a climb and a descent in a symmetrical pattern during each of the turns. At no time throughout the Lazy 8 is the airplane flown straight and level. Instead, it is rolled directly from one bank to the other with the wings level only at the moment the turn is reversed, the completion of each 180-degree change in heading. As an aid for making symmetrical loops of the 8 during each turn, prominent reference points should be selected on the horizon. The reference point selected should be 45 degrees, 90 degrees, and 135 degrees from the direction in which the maneuver is begun. Prior to performing a Lazy 8, the airspace behind and above should be clear of other air traffic. The maneuver should be entered from the straight and level flight at normal cruise power and at an airspeed recommended by the manufacturer or at the airplane's design maneuvering speed. The maneuver is started from level flight with a gradual climbing turn in the direction of the 45-degree reference point. The climbing turn should be planned and controlled so that the maximum pitch-up attitude is reached at the 45-degree point. The rate of rolling into the bank must be such as to prevent the rate of turn from becoming too rapid. As the pitch attitude is raised, the airspeed decreases, causing the rate of turn to increase. Since the bank also is being increased, it too causes the rate of turn to increase. Unless the maneuver is begun with a slow rate of roll, the combination of increasing pitch and increasing bank will cause the rate of turn to be so rapid that the 45-degree reference point will be reached before the highest pitch attitude is attained. At the 45-degree point, the pitch attitude should be at maximum and the angle of bank continuing to increase. Also, at the 45-degree point, the pitch attitude should start to decrease slowly toward the horizon and the 90-degree reference point. Since the airspeed is still decreasing, right rudder pressure will have to be applied to counteract torque. As the airplane's nose is being lowered toward the 90-degree reference point, the bank should continue to increase. Due to the decreasing airspeed, a slight amount of opposite aileron pressure may be required to prevent the bank from becoming too steep. When the airplane completes 90 degrees of the turn, the bank should be at the maximum angle, approximately 30 degrees. The airspeed should be at its minimum, 5 to 10 knots above stall speed, and the airplane pitch attitude should be passing through level flight. It is at this time that an imaginary line extending from the pilot's eye and parallel to the longitudinal axis of the airplane passes through the 90-degree reference point. Lazy 8s normally should be performed with no more than approximately a 30-degree bank. Steeper banks may be used, but control touch and technique must be developed to a much higher degree than when the maneuver is performed with a shallower bank. The pilot should not hesitate at this point, but should continue to fly the airplane into a descending turn so that the airplane's nose describes the same size loop below the horizon as it did above. As the pilot's reference line passes through the 90-degree point, the bank should be decreased gradually and the airplane's nose allowed to continue lowering. When the airplane has turned 135 degrees, the nose should be in its lowest pitch attitude. The airspeed will be increasing during this descending turn, so it will be necessary to gradually relax rudder and aileron pressure and to simultaneously raise the nose and roll the wings level. As this is being accomplished, the pilot should note the amount of turn remaining and adjust the rate of rollout and pitch change so that the wings become level and the original airspeed is attained in level flight just as the 180-degree point is reached. Upon returning to starting altitude and the 180-degree point, a climbing turn should be started immediately in the opposite direction toward the selected reference points to complete the second half of the 8 in the same manner as the first half. See Figure 9-5. Due to the decreasing airspeed, considerable right rudder pressure is gradually applied to counteract torque at the top of the 8 in both the right and left turns. The pressure will be greatest at the point of lowest airspeed. More right rudder pressure will be needed during the climbing turn to the right than in the turn to the left because more torque correction is needed to prevent yaw from decreasing the rate of turn. In the left climbing turn, the torque will tend to contribute to the turn. Consequently, less rudder pressure is needed. It will be noted that the controls are slightly crossed in the right climbing turn because of the need for left aileron pressure to prevent overbanking and right rudder to overcome torque. The correct power setting for the Lazy 8 is that which will maintain the altitude for the maximum and minimum airspeeds used during the climbs and descents of the 8. Obviously, if excess power were used, the airplane would have gained altitude when the maneuver is completed. If insufficient power were used, altitude would have been lost. Common errors in performance of Lazy 8s are failure to adequately clear the area, using the nose or top of engine cowl instead of the true longitudinal axis, resulting in unsymmetrical loops, watching the airplane instead of the reference points, inadequate planning, resulting in the peaks of the loops both above and below the horizon not coming in the proper place. Control roughness, usually caused by attempts to counteract poor planning. Persistent gain or loss of altitude with the completion of each 8. Attempting to perform the maneuver rhythmically, resulting in poor pattern symmetry. Allowing the airplane to fall out of the tops of the loops rather than flying the airplane through the maneuver. Slipping and/or skidding. Failure to scan for other traffic. End of Chapter 9. Recording by Dale Latham.